Hello and welcome to my talk. Let's see what's out there, mapping the wireless Internet of Things. So let me first introduce myself. My name is Tobias Zillner. I work as a freelancer in the IT security industry, and I'm also working for Cognizant as information systems auditor. So what I do most of my time is just penetration testing, any kind of security audits, security consulting. And in my free time, I love to do IoT security research, and I love to play using software-defined radio and assess any kind of wireless devices I get my hands on. So now I have a huge collection now of wireless toys. I'm always trying to reverse them and take control using software-defined radio. What I want to talk about today is, first I want to give you a brief introduction into the topic. So what is the wireless IoT? What are the problems in this area? Then I will just want to give you an overview how to do signal discovery, what helped me in the past a lot to find signals. I want to give you a short introduction how to get from signals to bits. I heard previously Michael did a more detailed view into this, so I will try to speed it up and talk more about the wireless security issues I found in the past and what I think during the wireless security assessment nowadays should be tested and what approaches are promising. And then I will just show you a short demonstration of a tool I developed that helped me finding signals out there and finding devices in the IoT, and how to take advantage of it and do then real testing. So what it's all about. The Internet of Things, everybody knows, it's now a buzzword at this time. More and more devices get deployed into this area, and wireless assessments are more and more requested. So I was struggling at the first time when I did assessments in this area because it's non-Wi-Fi, and I was just not aware of the unique characteristics of wireless devices in this area. So today I want to give you an idea how to perform assessments in this area and what I would recommend doing, or what helped me preventing mistakes in the past. So what is the wireless Internet of Things? So when you ask 10 people, you will find 10 different opinions, maybe, what is the Internet of Things, because it's a very wide area. What I want to talk about today is, for me, it's low-end devices. It's more low-power, low-cost devices that are connected, mostly battery-powered, using the wireless layer. Often these kind of devices don't have TCP/IP or Wi-Fi implemented, just due to energy-saving reasons. So they use different communication standards that are highly optimized for energy saving. Everybody now wants to try to make their physical devices smart, so this leads to several problems in this area because the manufacturers that build the physical devices don't have any knowledge about how to make secure devices and how to make them connected in a good way. So what I found, the biggest problem is, or the biggest issue is, in the past, they all relied on physical protection, but it's not enough anymore, because as soon as you connect them wirelessly, you don't have control over the physical layer anymore. When you have wired cables, it's very easy, so you can control who attaches a cable to your router. But the wireless layer, everybody can interfere and sniff the traffic, so just legislation keeps you away of interfering with the signals. The devices are also very limited, so they have limited resources like battery, processing power, or memory, and therefore also very limited reliability. So you need different ways of communicating. And unsecured devices are already rolled out, so this means it's for me, it's obviously very similar to the industrial control system. So you have products designed that are not made with security in mind and are now getting connected. So this is a problem, because also the lifetime is sometimes very long. So when you think of a home automation system, you want the lifetime of a home is more than 10 years. So it's 10, 20 years, and you don't want to change your stuff every 2 years like we do for example, using smartphones or laptops. So you have, they should be future-proof. And they are not managed, or managing is very different and difficult, because it's just a very high number of devices out there. So Gartner, for example, predicts that till 2020 there will be 26 billion devices out there. And they also said that during the next 10 years, every typical household will have 500 smart devices in it. So I don't know who will be managing 500 devices, even if it's not 500, if it's 50. I think that's too much for the typical end user. Who will do the updates? Who will do patching? How this is done? So do the devices even support updates? Nobody knows. But for me, it was also very interesting, beside from Gartner predictions, was that the Samsung CEO said last year that every Samsung device will be part of the Internet of Things till 2019. So this is more the company view and the real world. So it was very interesting for me to see. Also, security, I think, is a very important part to be aware of it now, because when we don't do it right at the beginning, we will have problems, the next decades. I brought today a quote from James Clapper. It's the director of the National Intelligence Service of the US. He's also a fan of the Internet of Things, because he obviously sees the benefits, like improving efficiency and more convenience for the user. But he's also aware of the downsides. So there are security problems in there. So researchers found a lot of stuff in the past. But yes, he works for an intelligence service, so he sees also a lot of potential. For example, identification, surveillance, monitoring, location tracking. So the more devices they get out there, the more or the better the network will be. And for example, for location tracking, will be really cool stuff. So also privacy is a huge concern in the Internet of Things. Just to illustrate the topic, there have been a lot of really big wireless fails in the past. So for example, think of GSM was vulnerable to hacking. RFID, NFC, also access control systems, credit card data, all was prone to hacks. A lot of car hacking was done in the past using the wireless attack vector. Traffic systems were hacked wirelessly. This is a quote from a German media. So I'm from Austria, Vienna, so we are very close to Germany, and also read their news. But for me, it was very interesting because they did a research and tested, I think, 20 keyless entry systems for cars, and all of them were vulnerable to a very simple relay attack. So the attackers just could extend the range of the wireless key and get entry to the car and just drive away. So that's a very basic one, but very effective one. A smart home system are also very vulnerable. So they were made for usability, but not for security. And one of my favorites was last month, the mouse check vulnerability. So it allows attackers to inject keystrokes in wireless keyboards and mice. So it's a very cool one and a very good example what the problems are and what could you test. We will see later on. So what are the biggest problems? From an assessment perspective, for me, when you get on site and would like to do a wireless assessment, you just don't know what is really deployed. So you don't know what protocols are used, because nobody knows at the company usually. Because wireless is often a blind spot. So maybe they know, or they will know about the Wi-Fi and the access points, but everything that's not connected to IP is very often not just included in network diagrams. Nobody knows. They know maybe, for example, the gateway, because it's still connected to IP, but the sensors that are connected to the gateway, nobody is aware of that. I also see a big knowledge gap. So I experienced myself when I got into the topic, I think 2 years ago. And at first, I tried to rush into the topic, but I was not aware of the basics, like RF, software-defined radio, and signal processing. So the physical layer, you need to be aware of. And there is also a lack of tools, so it's very hard for security testers to yeah, there are no commercial tools out there for testing this stuff. There are a lot of open source tools out there, but they are not very mature. So the knowledge gap, there are different technologies and standards are used. There's stuff like Zigbee, Z-Wave, 6LoWPAN. There are really a lot of stuff, and a lot of stuff is currently in development for the wireless IoT. A lot of proprietary protocols are used, so you have to do a lot of reverse engineering. A lot of research has been done. There are not really a lot of industry standards that are followed, and even if they are, maybe a lot of companies just add some custom bytes there so that their products are not working with different vendors anymore. So they want to try make closed systems. And when you get on site, you have just no knowledge about what protocols are used, what is going on in the radio, and nobody knows what is out there, and you don't know how to detect it. Yeah, again, lack of tools. So in the past, some researchers made some prototypes, but they're often just built for one specific use case and for one specific device and system. They're not maintained anymore, a lot of them. They're poorly documented, a lot of bugs are in there. So I released a tool for Zigbee testing my own last year, and this is all applied also to my tool, so I just released it. And then after some time, again, I started to do some bug fixing and stuff, but we should stick to our tools and try to, if we release stuff, do a proper release. Do everything we usually mark as a finding during a source code audit. We should do it ourselves, but I experienced a lot of guys like me. We are not software developers. We just script and code some stuff, and it works, and it's fine for us. But we should invest more in this area. And even if you have tools, I think you need a different methodology to test the stuff out there, and you need some custom test scenarios and be aware of the attack vectors that are specific to this area. Okay, then let's step into it. So how do you discover signals? For me, it's like, when you compare it to traditional penetration tests, it's like the information gathering phase. So I just need to find every stuff I get, which makes it then easier in the later on to create or get packets out of it or whatever. The first stuff I would recommend is doing interviews. Just talk to people. When you go on site and to say, okay, we want to check our wireless attack surface, just ask the people, and maybe they remember what protocols they use, what devices they deployed. Maybe they had some interference issues. They said, okay, we had to move the devices because we had interference with Wi-Fi. So you know, okay, maybe it's in the 2.4 gigahertz band or 5 gigahertz band. Let's check this more in detail. Interviews are always very promising. If you get your hands on the device, obviously check the FCC ID. So every device sold in the US has to be checked by the FCC and gets a unique identifier. And using this identifier, you can get a lot of information. Like you know what frequency is used or what frequency band. You get also a lot of additional information, like pictures of RF chips, if you're lucky. You get manuals, you get test reports, you get really a lot of supporting documentation. And if you're lucky, you find even an emission designator. So emission designator is very cool because it specifies the bandwidth used, the modulation type used, how many channels there are, and even what type of data is transmitted. And what cool stuff you can do is then some guys already mapped some emission designators to typical applications. So you can look up your emission designator and say, okay, this pattern is usually or is also used for this kind of protocol. That's very helpful sometimes. Yeah, Google is also a very good source of knowledge, but just also search for patterns. There are some custom search engines for pattern search. Use them, because a lot of times you will find packet structures described, you will find workflows in there. Not the real details, but it will help you understand what's going on in the radio. So check also patterns. Yeah, product documentation. If you find a manual, a lot of times there is the modulation type specified, the frequency it operates on, so it's really helpful. When you know what RF chip is used, that's a really great success because sometimes they use coprocessors for crypto, and then you know, okay, what is this chip capable of? What modulation types does it support? What data rates? When you get your hands on the firmware, you even find the configuration of the RF chip, so you know it definitely what is applied or configured. So, for example, this is a Texas Instruments chip, and you will see there is described what frequencies are supported, what data rates are supported, or what modulation types are supported. This helps you a lot if you have this information, because otherwise it's always, yeah, a guessing game and try and error. If you don't get any of this stuff, you will have to stick to visual signal identification. So we'll just have to guess some frequency bands and just go through it and see if there is any communication going on. There are a lot of tools out there that help you and visualize it very nicely. I would recommend using InSpectrum, Baudline, Phosphor, and yeah, GNU Radio, which is the best one, I think. I would also recommend to have a look at the signal identification wiki, because there are a lot of signals already identified. So when you find a pattern or have a waterfall, you will be able to match it. So you just look it up and see, okay, is there already an identified signal? I don't know, and the waterfall is very similar. So because then you know what protocol is it, what data rate is used, what modulation type is used, and that maybe helps you to recreate a decoding by yourself. Also, legislation helps you sometimes, because certain frequency bands are allocated for a specific purpose. For example, if you test a hospital, it might be worth checking the medical frequency band. So there is a certain frequency band allocated just for medical usage. Just check it. I'm not aware of the legislation in Singapore, if you are allowed to do it. In Austria, where I come from, it is allowed as long as you don't do any harm or don't have the intention to get any profit out of it. So for research purposes, it is fine. Yeah. So then after your initial information gathering phase, you have a signal or no, okay, at this frequency there is something happening. So, but we want to now then get to our digital bits. So we want to make an analog signal to digital bits. I want to give you a short example how this is done. I want to, yeah, was a reverse engineering of a power plug. I have of my own, and it was quite helpful because the frequency is printed on the power plug. So this was my first information gathering phase. So I knew at what frequency the device was operating. So what I did then is just I built a GNU Radio flow graph and made a graphical sync and checked the frequency range. And you see in the center there are some spikes popping up. That's very cool because I think that there are transmission bursts in this area. And when you zoom in, you will see, okay, you have a strong signal and a certain bandwidth. So this means in this case it's from -50 to 50. So okay, I think yeah there is the most action going on. So I should isolate the channel there and get rid of the interference and the noise. So this is a very important step. Do filtering and get rid of any interference and noise you can get, because what it looks like then afterwards. So I used a low-pass filter and set the cutoff frequency to 50, we identified before, and you get a much cleaner signal then, and you don't have any interference at all, but the data is still in there. So you see, it's the same bursts going on. So we now have identified where the power plug is working on, and we have specified the data channel. So now we have to identify the modulation type. I wasn't aware of it before, so I just did a capture and loaded the capture in a tool called Baudline. I rotated the window a little bit, because usually it's from top to down, but I think this way we can see it better. From left to right, it's time. and from bottom to top, it's frequency. So you see, the frequency is shifting over time between two frequencies. So that's a very strong indication for a modulation type called frequency shift keying. And it's also just shifting between two frequencies, so it's most probably 2 FSK. There is an easy way to decode or demodulate this in GNU Radio. There is a block called quadrature demodulation block. What it does is just taking a complex signal and calculate on the output is then calculation of the phase difference in the signal. So you would see frequency changes in the output. What I now did, I just changed the graphical sync to display this frequency changes. So what we now see, I stopped the flow graph, so we have a better look at it. And you will find, okay, this is very similar to the one we found before, but now we are able to process the data and work on the signal. So that's a very important step. But to get to the logical bits, we have to identify the data rate and the baud rate. So for my power plug, I just did some research what it's using. So it's using C-Wave. And in C-Wave, you have two different common data rates, it's 40K and 9.6K. So I built this into my block very easily because I knew it before. But you can also do a signal, a visual inspection, which makes it very easy. This is a zoomed-in version of the signal. And you see, between 5.6 and 5.7, this is one symbol is transmitted. So you know you have 0.1 milliseconds per symbol, and then you would just have to calculate using your sample rate how many samples you have to process to get to one logical bit in the end. So that's a very important step for clock recovery then, because you will have to get from data samples back to logical bits, and you have to specify in a block called clock recovery then how many samples per symbol have to be processed. So what it takes now 83 samples as input and tries then to make a guess if it's a 1 or a 0. I also included a low-pass filter before just to clean up the signal. So, okay, we now have our raw output symbols, and we want them to get to logical bits. There is some encoding you have to do. There are a lot of different versions of encoding out there, so it's a lot of time it's just try and error, or not only try and error, but there are some different types. So for example, there is non-return to zero, which is a very simple encoding type, and you can have long sequences of zeros or ones in there. So if you see it in your raw output, maybe just try variations of NRC encoding. In our case, it's used Manchester encoding, so there you won't find long sequences of zeros or ones. Or you could also do pulse width modulation, so you see a long pulse for 1 and a short one for 0. So just have a look at the signal, read into different encoding types, and then just try it out. So that's no easy way. But we know ours is Manchester encoded, but because we identified the protocol before, and so we are able to build or to get to the logical bits. So the next step is then how to get from the raw output to the packets. So just analyze your output structure. So find patterns, do pattern search, identify starter frames, end frames, and indicators, search for a preamble, sync words, search for known values like serials, numbers, identifiers, module names, manufacturer names, hardware addresses, everything you know, just check if it's somehow included. Also, a very good guess is always at the end of a packet, very often as a checksum or error correction and detection code, because wireless is is not a reliable transport medium, so you have to do error correction most of the time. Also search for repeating changes like counters, sequences. So if one part of the packet always stays the same, maybe that's an identifier or an address, and the next bytes are always changing, maybe that's just counters and sequence numbers. Also check, is the packet length fixed or is it variable? So if it's variable, maybe search for the packet lengths. So these are just my recommendations that help me a lot to do it. When you have figured out the packet structure, you are able to build a custom radio block, a custom sync. I was just using then the C-Wave block already included in a framework called Scapy Radio to interpret my raw output and get to the C-Wave packets. So this is how it looks in action. You see the bursts coming in, and on the left side you see, okay, there is data changing. You see as the bursts come in, the data changes. So we're now successfully able to get the raw C-Wave packets out of it. It was just a very very fast process. And here in the real world, it is much harder because you don't know a lot of stuff. I would recommend to everybody doing this. So I started doing wireless assessments, I think 2 years ago, and I made some mistakes. So I rushed into the topic very fast. So I didn't have my basics right. So I thought, okay, it's maybe easy, just graphical interface, just put some blocks there and connect them, and it will work. But you will make a lot of stupid mistakes. So I would recommend to everybody, get your basics first, learn about RF technology, learn about software-defined radio, signal processing first, get familiar with modulation types, what is sampling, what is used, where are the pitfalls of sampling, get to use how complex numbers are used, because a lot of signal processing stuff is done using complex numbers, and it will be much easier for you if you just understand what is going on. When you do captures, always store metadata, because my memory is sometimes not the best, and I forget just how I set the capture rate, the frequency, or just even the gain. It's always worth about storing it. Choose a proper RF gain. So first, I was very tempted to just set the gain to a very high level because I always thought, I get a stronger signal. But in reality, what you get is more noise and more interference and not a stronger signal. So just try to find a proper level of gain to get a clear signal, but not too much interference. Know your tools. This was also a very hard one for me because there are some visual resolution problems at tools, maybe for example Baudline. I always thought setting the FFT size, so that's more like the resolution of the tool, to a very high value will give me a better view of it. But that wasn't true, because this, for example, is very blurry, but it should represent the C-Wave packet we've seen before. So, and the FFT size, the resolution is at a very high level. But when you set it to a very low level, you will see again, okay, when you zoom out, you will see the signal and the changing of the phase or the frequency more clearly. So this helps you a lot. So be aware that also these tools used for visual inspection are not very mature and have a lot of, not bugs, but you need to know how to handle them. Always a good recommendation is check what signal you are really analyzing. Because wireless is not stopping at your walls, so check that you're not analyzing the signal of your neighbor. So just move around and see how the signal behaves. So if it gets stronger, if you get closer to the device, you're on the right track. Use filters. Check that the signal is in band and not an alias. That's very important and will make you confusing if you don't use filters. Really do filters. Timing is also a very important issue in wireless communication. So clock recovery is a very important point to get to the bits. And also for sending, it is very important. Transmissions, message timeframes are really, really important to get. So I had big issues with timeframes at sending last year. So read and understand the protocol. Are there any timeframes you have to apply? So it's just a couple of references that helped me most during the last 2 years. So there are a lot of cool talks at the Wireless Village at DEF CON. I would recommend to everybody watching the video series of Michael Osman at greatscottgadgets.com. It's really easily explained. Wikipedia is your friend for encoding types and RF theory if you just need a quick look. Yeah. So what security issues I've identified in the past? So this is more recommendations. What test cases should you apply and what should you test? Because the wireless is mostly designed for other purposes. So there are a lot of possible security issues in there. So it's designed for energy saving and for robustness. So the user should not do a lot of stuff to get the devices up and running, and they should be out there with any manual work to be done a lot of time. So this is my personal wireless IoT top 10 issues I found in the last time, and I think it's always worth checking it. So obviously the first one is check for unencrypted communication. So because when it's unencrypted, it's very likely that there is no security at all, and you have an instant win. Check also for known protocols out there. So if you already know the protocol, maybe there is a tool already out there that helps you testing it. And if you have an unencrypted communication and have a tool, you instantly are able to take over the network most of the time. Replay attacks are also very promising and a very good indicator of the security level of the system. So if you are able to replay stuff, it might be that the security is not that mature. And you can also do replay attacks for encrypted networks. It makes it very easy. Just capture it, replay it, and see how the signal how the system reacts. Key exchanges are often vulnerable. So this means when you do encrypted stuff, the keys have to be transported, but most of the time it's just also sent using radio, so it's an in-band key exchange, and a lot of times it's done in plain text or using publicly known keys just to ensure that devices from different vendors work with each other. So for example, Zigbee is using most of the time default key material to exchange keys. Also Z-Wave has the same issue. So all protocols are struggling with key exchange because nobody wants the user to attach a cable or scan a QR code or that kind of stuff. Jamming, most of the time, successful because you can't prevent it, but you can detect it or make any other measures. For example, I'm able to jam my motion sensor at my smart home at home. So I just do jamming and I don't get any notifications anymore. This means I can break into a house and I get no notifications because the alert is just jammed. Very promising and funny is always just mixing encrypted and unencrypted communication. So if the wireless system is using encryption, just try to inject unencrypted messages, because a lot of times, a downgrade of the security level is successful because it's just accepting all data it gets as long as it's a valid packet. For example, the mouse check vulnerability is using this kind of stuff. So the dongle and the keyboard are communicating encrypted, but the dongle accepts also unencrypted messages. So that's very cool because I don't have to bother how to get the encryption keys. I just send it unencrypted. So that's always worth a try. Pairing procedures or joining to a network, always very promising. Because usually you set your gateway into a pairing mode and then allow devices to join, but you don't have control who joins because you don't control the physical layer. Usually you would just control who attaches a cable to your router, but in the wireless world you can't, so you set your gateway to enable joining, and maybe also an attacker joins your network. But if you're lucky, you see it in the gateway and can remove it again. But maybe it's too late because he already knows the key material, and then you have to do a key rotation and kind of stuff. I often found also systems that enable pairing or joining all the time. So just try to join the network and get the materials. So it's a good choice. Hard-coded secrets, very dangerous because IoT devices are very often not built tamper-resistant. So if you get your hands on the device, you can maybe read out the memory and get every hard-coded secret. And if a vendor applies the same secret to all of his devices, then you have a win. Weak cryptography. We as a security community know doing your own crypto is not the best idea, but a lot of other manufacturers don't know it, and they try to come up with their own stuff. Message authentication. Spoofing, message spoofing, nearly always works, because even if they apply encryption or a security level, often they have it at the network level. This means every device is sharing the same key material. And so you don't have any possibility to ensure who is originated or who sent the signal and the message really in the real world. So if I manage to get onto the network and have the key material, I can impersonate every device on there. Also, rejoin procedures are I think, a very special attack vector to wireless IoT, because the devices are very unreliable, and you often ran out of battery, or just, if you think of wearables, you go out of your house and come back in, and then you have to rejoin the network. And maybe the network key changed in the meantime, so you don't have valid cryptographic material. Turned out, I recently found out that Zigbee is using such kind of insecure rejoin procedure, and I will talk about it more in detail later on. But in the real world, it's just try to rejoin networks spoofing known devices. That's also a very good approach. So now I want to give you a short demonstration how you could do such kind of assessment in the real world. So I built a tool which helped me a lot finding signals or finding or identifying protocols, because otherwise you would have to do a lot of visual signal inspection, a lot of try and error of random tools, just fire it up and see if there is any stuff detected. So I thought maybe build one tool just for discovery, and then you are able to switch to a more dedicated security testing tool. So it's more like a wireless IoT device scanner. It's based on Scapy Radio, and what it does, it just checks, you can configure it and scan all channels per protocol, and you can for known devices. At the moment, it's just passive sniffing, but I also want to add, during the year, active scanning. That's more like a radar sending out a beacon and then listen what devices react and are out on the channel. I tried to make it very easily expandable, because I think that we need such kind of a tool for initial discovery. Like we have, for pentests, we have port scanners and network mappers, and I think it would be nice to have it also for the wireless stuff. How does it look like? For example, yesterday I did such kind of a scan in my hotel. And I just configured, because I think maybe it's using a building automation system. So I scanned for Zigbee and Z-Wave devices, and I was successful. So as you see, on Zigbee channel 20, a device was found, and then another packet was received, but it was invalid, so maybe I was out of range and I just had some parts of the packet right. And I also found a Z-Wave device operating at the frequency 868 megahertz. So how does it look like, the application? So it's just you fire it up, and for example, Zigbee has 26 channels, and I don't want to scan all the channels because most of the time it's just using the preferred channels. So I configure the possibility to do a fast scan and just check the most common channels and frequencies. And you see, okay, it's then starting at channel 11 for ZigBee, listens for traffic, then channel 15. See, okay, there is some stuff going on, and also channel 20, and there is also a device operating at channel 20, which is interesting because it's a short address 0, which is usually the central gateway. Okay, so now we found a device operating on channel 20. That's really cool, because now we can switch over to a more dedicated security testing tool and try to do more nasty stuff. And as mentioned before, rejoins are always interesting way of how to test stuff. And ZigBee describes such kind of an unsecured rejoin process in the specification. So you see, a device is able to trigger a rejoin request, which is unsecured, and you will get then, or trigger a key transport, which is then also unsecured. And so this is a way how to get key material without any knowledge of the active network key or any prior knowledge. So you can just get the stuff needed for this kind of attack out of sniffing the traffic. So you just need MAC addresses and that kind of stuff. Then you can build your packet and just spoof a device rejoining. So I used ZigBee for testing this rejoin. It's a tool for ZigBee security testing I developed last year. And this is how it works. On the right side, you see the graphical user interface. On the left side, it's Wireshark, just for a better, to get a better view of the traffic going on. You see there's the first packet in there, and you see, okay, there is stuff going on. Then I just choose the source device. This is the device I want to spoof to join, and the destination. And I then say, okay, I want to impersonate the device and say I want to do insecure rejoin. So I press the button for insecure rejoin, and you will see instantly the rejoin message transmitted. And then there is a lot of stuff going on, which indicates, okay, the packet was accepted and was successful and triggered the key transport. And we will see, okay, or we will not see because the resolution is not so good. The key was transported. So this is a more detailed view about on Wireshark. Wireshark has a built-in ZigBee dissector, which makes it very easy and nicely to understand what's going on the network. So you see there was a rejoin request sent, and the security is set to false. So there is no encryption applied for rejoining the stuff. What you will get back is then the active network key, just encrypted using the default trust interlink key. So it's then a known key for ZigBee. Actually, it's ZigBee Alliance 09, so you know what in what year the specification was done. I was very excited after I found this kind of stuff, because now it enables me to get key material every time I want. I don't have to wait for users pairing or joining to sniff traffic. I can trigger it whenever I want. So this was very, a breakthrough for me. And what you can do is then just inject commands and take over control of devices. So that's our test setup in our lab. We have a door lock board and a smart home system. And first, I just open it and close it using the smart home app. You see here, I set it to green. It's locked again. Then I just impersonate now the gateway and send a unlock command using ZigBee again to the door lock, and it's open. And we're not using the smart app. See, the software-defined radio boards we use for transmission of the signal. So that's very easy. So I can now break in to smart homes if I want. The funny it is for a security researcher, when you deal after some time doing wireless assessments, you think, why do they do it again? Because there are mistakes made decades ago, but with the same mistakes are made again in the IoT because just the vendors producing the stuff just don't have experience in it. They don't have experience making devices smart, so they're making it more dumb. They just try to any way connect it and make it build some features for users, but security is not included at all most of the time. So just want to summarize it up. So think of wireless as a huge attack surface. So it just depends on what receivers and transmitters you use. And most of the protocols use mesh networking in this area. So this means the more devices they get out, the more the range of the network will be extended. And it will just, when you, for example, test an industry site, and you have a network in the middle and the center, and from the edge of the power plant, for example, you can't connect because you're not in range. But then if you have more devices at the end and maybe a light bulb at the edge, and you just see the range of the light bulb, you just connect to the light bulb, and the light bulb will take care of relaying the signal to the actual network. That's very cool. So usability overrules security in this area. So it's very important to bring features out there. It's a battle for market share at the moment. So every vendor wants to build cool devices, cheap devices, and make safest market share there. There are a lot of attack vectors out there. They are very different to traditional Wi-Fi, for example, because just that devices have other resources than traditional notebooks, smartphones, or whatever. I also want to encourage the community, do more research. It is a very funny field of research because you will find a lot of stuff. So it's not like doing the billionth penetration test of known web servers again and again. But go do reverse engineering a proprietary protocol, you will most likely find some really cool stuff. And try to bring out some tools, because it is very hard to do reverse engineering all the time. Especially for a penetration test, you have limited resources and limited time, so you need some stuff. Reverse engineering is not the way to go during a penetration test. So get the low-hanging fruits, check for known protocols, known weaknesses. Reverse engineering is more a part for research most of the time, as long as it's not very, very basic. So just want to remember there is a world beside TCP/IP and Wi-Fi. Be aware of it. Security is often not mature, so it's a big issue in it. And be aware of wireless communication is also an attack vector. It's not just Wi-Fi, it's wireless keyboards, wireless mice, it's building control systems, access control system, whatever you can think of. Every company now is getting more and more wirelessly connected, and it's often a blind spot in security strategies. Okay, thank you for your attention. I will be around all the day long, so, but if you have questions, just ask them now. I would be happy to hear. Thank you. Any questions? Great. Thank you again.